Hello and welcome to the presentation of our senior design project. We are team 19065 and our name is Dairy Animal Detection and Environmental Control. We'll start by introducing the team members that are listed here, starting with Ziad.
Hello, I'm Ziad Al-Lukman. I'm the team lead for the project. I'm majoring in engineering management.
Hi, I'm Angel Ortiz and I'm the mechanical engineering on the team.
And I'm Micah Mann. I'm the optical science and engineering major.
Hello, my name is Jordan Barakat and I am an electrical and computer engineer.
Hi, my name is Juan Romano. I am an electrical engineer on the team.
The purpose of this project is to create a cost-effective camera system able to detect and report the populations of birds in a feedlot. Birds are more than just a nuisance in Arizona dairies. Through selective feeding, they consume proteins and nutrition that are a necessity for cows to function. This is harmful to the animal's health and milk production and only creates a financial loss for the dairy companies. Our objectives for this project is to create a cost-effective camera system capable of detecting and reporting the population of birds. Our next objective is to create a website that we can report the data to the farmer. And then we must also have manual software design documents, system design documents to give to the sponsor.
Considering all of our objectives, we thought about all the parts that were necessary to accomplish our goal, and we invested our time into thinking about the three main components, which were the camera, the website, and the housing, and how they would all fit together. And so once we had done research to think about the software, the housing, and the camera, we then focused on the system as a whole. Upon initially starting the project, we knew we needed a camera to view the birds and a CPU to run the algorithm and transmit the data to our website. Our main two choices for the CPU were a Raspberry Pi or an Arduino, and we chose the Pi because we were considering using a Raspberry Pi camera accessory. And so our sponsor actually suggested the JBWA because it had built-in facial recognition and library resources to help us that we thought we could complete our project with. So the JBWA can use either TensorFlow or OpenCV, and we ultimately decided to use OpenCV because it was easy to learn and had the capabilities to fulfill our project. And so we also talked to our sponsor about housing, and he talked about how 3D printed housing wasn't good for the environment, so we decided to use CCT camera housing instead. After reviewing all of our options, we analyzed them based on our factors, which were cost, feasibility, size, and weight, our own knowledge, duration, and our sponsor's request. Using these factors that are listed on the slide, we came up with requirements that were necessary to meet our goals and our objectives. We added a camera mount to prevent the camera from becoming misaligned and losing data. We added a fan to ease the strain on the Raspberry Pi and the JBWAs due to heat. Testing of the website was performed on a free Amazon web server to observe its functionality and make sure there were no errors or unexpected results. We then transferred the files over to the sponsor's created server.
The next slide will be going over system requirements that have 6 categories. These categories are performance requirements, environmental control, optical properties, mechanical requirements, customer constraints, and design features. Below each category, there are sub-requirements that we'll be going over throughout this presentation. On the next slide, there will be the next 3 categories. The main requirements on these lists are the weight, off-the-shelf technology, and the cost.
After we mapped out our approachment using our requirements, we applied them to our project. The 2 main components were decided to be a Raspberry Pi 4 and a JBWA smart camera. Through the next 2 slides, we'll look at a DADEC risk analysis table that sets the cornerstone for us to pick our camera. Our camera options varied between a Raspberry Pi 4 and its multiple configurations or the JBWA smart camera. We measured our decision based on risk using a weighted point system. Features like quality and software implementation were important to us, so we weighted them as 8, while things like complexity were not as important, so they were weighted as 6. After deciding on score for each category as a team, we came to the conclusion that the JBWA Smart Camera came with the least risk with a score of 127.9. And this is the reason why we chose it. At the time, it boasted a 60-degree field of view, 10 degrees more than the Raspberry Pi 4 camera. This was very convincing to us as it was listed in the spec sheet, but later we will measure the field of view ourselves.
To meet our system requirements, we will conduct tests, analysis, demonstrations, and inspections and set the margins to ensure it passes. For our requirement verifications, we perform these tests and analysis we listed here. Here's what we'll demonstrate and inspect. Feel free to pause the video to view these verifications. Finally, we will talk about how setting the margin for the CPU temperature of each of the devices and decide if it's within the margin. Next, Angel will be talking about the results.
For our results, we were able to test the CPU temperature, the field of view, and the accuracy. However, we were unable to test the dust resistance, bird feces, and corrosion resistance due to the coronavirus outbreak. For our CPU temperature test, we placed the complete housing in an ambient room temperature of 85 degrees Celsius and measured the CPU temperatures periodically. For the first figure of the Raspberry Pi, we noticed that the temperature reached a max temp around 47 degrees. For the next slide, we noticed that the JBWA's camera temperature rounded off around 6 degrees. The takeaway message would be that the CPU temperature of the Raspberry Pi and the JVOS camera both passed the test and reached the max temperature of 50 degrees and 60 degrees Celsius, while the overheat temperature values are 81 and 71. And neither will overheat.
For this slide, we tested the accuracy of the object detection algorithm versus the real life, which this test consists of taking a frame and running it through the algorithm, then having one of the team members count the birds in the frame and see how the two compare. Based on results shown here, the object detection algorithm had an adequate accuracy, but it has certain limitations. When we place a picture of a chicken up close, both the team member and the computer algorithm can detect it, but when we tested the image of the pigeons, we can see that the detection algorithm only detected a fourth of what the team member counted in the image. You will see this demonstration later on in the presentation. Listed are two cameras, Cam 1 and Cam 2. We measured the field of view of each camera by hooking them up to a laptop and pointing it at a whiteboard. Then we marked on the whiteboard the edges of what the camera can see. With basic trigonometry, we extracted the horizontal field of view of each camera and averaged them to get a value of 50-degree horizontal full field of view. I mentioned earlier that the 60-degree horizontal field of view was in the spec sheet and is what attracted us to the JVOL camera. This was disappointing, but it did not entice us to change our camera because its field of view now matched the Raspberry Pi 4 spec sheet and remained relatively compact and cost efficient. The reason for the field of view test was so we can optimize the camera area coverage. Since we measured the horizontal field of view to be about 50 degrees, we can use the aspect ratio given by our pixel dimensions to determine the vertical field of view, estimated to be about 40 degrees. With the camera placed 13 feet high, we get a horizontal coverage of 12.12 feet and a vertical coverage of 9.46 feet, giving a total area coverage of 114.6 square feet. To optimize the camera placement, the camera should be placed about 12 feet apart. One more note is that the distortion was measured of each camera to be about 0.1% of barrel distortion. Therefore, the edges of the camera frames remain sharp in image quality.
Data reduction is very important due to the large scale of our project with all of the data we will be taking over time. So the home page will display the average data across all the cameras, and on the side you can select to view one camera specific data. We've also allowed for the data to be viewed hourly, yearly, and daily, with the date and time being selected by the user. And we've also added a feature to delete an old camera's data so that we can prevent cluttering of the database and showing old data, but the data will still be saved on the local CSV file of the SD card on the Raspberry Pi.
Our deliverables consist of 6 main packages: a software design document containing the detection algorithm in an easy-to-read PDF format, code files as a master directory in various coding language. This is our main code containing not only the algorithm, but the software as well. And more physical things like the technical data package so the cameras are easy to maintain if damaged or malfunction. Lastly, we are delivering a full camera unit.
Next, we'll be showing a demonstration of our camera system. For our object detection algorithm demonstration, we'll be showing its limitations. We have an image and video object detection algorithm. Due to the fact that we are unable to implement our camera system with real-life data from the feedlot due to the coronavirus outbreak, we used the videos from online. The object detection algorithm uses characteristics to determine if it's a bird, like feet, legs, beak, wings. The next slide shows a CAD drawing of how we ensured that the 3D printed mounts would fit in assembly before printing. The picture on the right shows a real-life assembly of the internal components in the housing. This is what the camera housing looks like with the arm brackets supporting it. This video is our video object detection algorithm running on birds walking across the street, and we can see that it does not detect every bird in the frame. Video is a chicken, and we can see that it detects the bird with 90% accuracy. The next slide shows an image provided by our sponsor that was then ran through our object detection algorithm. We can see that the resolution of the image isn't the best, and the birds blend pretty well to the background. The image algorithm also detects a cow on the right-hand corner, which we could see its limitations. Due to the image quality, the algorithm cannot see the characteristics of the birds, like its feet or wings. It just sees a blur or dot and can't pinpoint the characteristics.
Some surprises we had for this project were the field of view being incorrect on the spec sheet, virus situation, and mainly difficulty of the detection algorithm. We learned we needed to work more as a team and get help when needed. Lastly, we were relieved that we were able to get past the detection algorithm along with an online-only lifestyle. We made sure the cameras were placed in a safe location not to injure workers at the feedlot, and we considered and mitigated the dusty feedlot and issues such as overheating and low resolution.
This finalizes our presentation, and I would like to thank you for watching.